We can test for the presence of a carbonyl group, whether it's in an aldehyde or ketone, by reacting our molecule with 2,4-dinitrophenolhydrazine, better known as 2,4-DNP. In practice, 2,4-DNP is dissolved in methanol and sulfuric acid, and it's commonly known as Brady's agent. A positive result gives us a yellow-orange precipitate, which indicates that the aldehyde or ketone has been added to the 2,4-dinitrophenolhydrazine. This reaction takes place via two steps. Firstly, nucleophilic addition, and secondly, a condensation reaction. I'm going to run through the mechanism for each stage in this reaction, not because you'll ever be asked to reproduce it, but because it showcases a number of key reactions that are common in organic mechanism. If you simply learn each mechanism as we go through A-level chemistry, parrot fashion, then you'll find that when you get to the exam, it all becomes a big muddle and a panic in your head. It's much better that you have a genuine understanding of how atoms and ions behave during mechanisms, so that you can apply this in unfamiliar situations. 2,4-DNP is a nucleophile. We know that because it contains nitrogen atoms. Nitrogen atoms have lone pairs of electrons, and lone pairs of electrons are very keen on attacking delta-positive carbon atoms. So here we go. We can attack the carbon atom, and the electrons from the double bond move on to the oxygen. Oxygen is electronegative. It's more than happy to carry a negative charge. This lone pair of electrons is now a bond between the nitrogen and the carbon. And as we can see, the result is that nitrogen is now carrying a positive charge because it's making 4 covalent bonds. It's lost its lone pair. The oxygen which took on a pair of electrons is now negatively charged. The easiest way for nitrogen to regain its lone pair of electrons is to kick out a hydrogen, and that's exactly what it does. The hydrogen is kicked out, and the electrons from the nitrogen-hydrogen bond return to the nitrogen as a lone pair. Once again, we're being very careful with the way we draw our arrows to show electron movements. So as we can see in the next intermediate, our nitrogen has got its lone pair of electrons back, it's lost its positive charge. The oxygen can neutralise its negative charge by forming a bond to a hydrogen ion, and the result is an OH group. The reagent 2,4-DNP is acidified, which means that oxygen can do what it likes to do best. It can use its lone pair to attack a hydrogen ion from our acidic solution. The OH group is now an OH2 plus group. Essentially, it's water. Water makes a very good leaving group. And we find that oxygen takes the electrons out of the carbon-oxygen bond and leaves. The carbon, of course, will then only have 3 bonds. This can be solved by nitrogen using a lone pair of electrons to form a double bond between itself and carbon. The result of which is that our nitrogen is now making 4 covalent bonds and is carrying a positive charge. How does it get rid of that positive charge? Well, we've already seen. It simply kicks out a hydrogen and nicks the electrons. So here goes. We can just about squeeze that in. And our final product molecule is our yellow-orange precipitate, indicating that there was a carbonyl group present in our original molecule.